So here we'll discuss the correlation functions. We will see that later on that these functions are quite useful in comparing or correlating two signals. They are also used in formulas for the calculations of energy spectral density and power spectral density. So let's move ahead. So the problem scenario that we have is we transmit a signal GT from this transmitter antenna towards a target, and then we have a received signal ZT that is reflected from the target and received here. So now our aim is, how do we know that the received signal is a reflection of the transmitted signal, because there can be many signals received at the receiver from different sources. And the second thing is how to determine the distance of the target. So with this background, we'll see how correlation helps us in solving this problem. So first we'll see what is the relation between signal and vectors. Once we have established that relation, we can then apply the operations that we apply to vectors. They can also be applied to signals, and this makes the calculation quite simple. So we'll see that there's a strong connection between signals and vectors. To prove this connection, let's say we have a signal that has been defined for only finite number of time instants. Say that number of time instants are n. So let's say the signal that we have, the continuous time signal is gt, and it's defined over an interval from time t is equal to a to time t is equal to b. Now, since we have only n points between these two time instants a and b, so these points are uniformly distributed in the time interval ab, so such that we have t1 as a. The next time instant t2 is there is an incremental quantity epsilon that we add to a, and this goes on until we have Tn, which is a plus n minus 1 into epsilon. So that would be the final point b. So between a and b we will have a total number of points n minus 1. The total number of points within this bracket is n. So the last point before b, or the last point at b, is n minus 1 into epsilon plus a. What is the value of epsilon? Epsilon is the difference between the final point minus the starting point and divided by the total number of points between the start and the end. So then if we have this distribution of the time instants t1 up to tn, when we substitute these time instants in the value in the formula for gt, or we sample the gt at these time instants, so we get an n-dimensional vector starting from t1 up to tn. So as the number of time instants n increases, the sampled signal g will grow. So as you this can be this is easy to understand that if n is large, then our this vector consisting of the samples of gt would be large. For n infinity, the signal values will form a vector g of infinitely long dimension, and in that case, if n approaches to infinity, epsilon, the distance between 2 points in time, would approach to 0. It will be very, very small. So the vector g, this one, will transform into this continuous time signal for this limit n approaching to infinity. So this vector g and gt, they will almost become equal when n approaches to infinity. So we can write this in an expression form like this. So now this implies that continuous time signals are straightforward generalizations of finite dimension vectors. So from this discussion, we now can see that continuous time signals and vectors can be related by choosing appropriate number of samples. So the basic discussions and operations in a vector space can be applied to continuous time signals as well. So this is the this is the implication that for the operators that we apply for vectors, they can also be applied for continuous time signals. So we shall denote all vectors by boldface type, like you can see this is the bold font. X is a certain vector with magnitude or length will be defined with this representation. So in a vector space we can define the inner or dot or scalar product. So we know if we for vectors we have this product which is generally called dot product of two real valued vectors g and x and norm x. So norm is the magnitude of a vector. So that can be, so the dot product can be represented generally in literature, it's represented like this: g comma x, and then it's equal to magnitude of g multiplied by magnitude of x and the cos of the angle between g and x, where the magnitude square, if we have both, if g is equal to x, then this term becomes x magnitude squared. So as I said, theta is the angle between g and x. So the idea is that if we have if we can relate continuous time signals to vectors, then we can apply these scalar and dot products to the signals as well. So a component of a vector along another vector. So now the first task was to establish the connection between signal and vectors. Now we'll review some of the properties of vectors. So first one is the component of vector along another. So here you can see we have a vector x and we have another vector g. They are at an angle to each other. So the component of g along x is represented by cx, right? And geometrically the component of g along x is the projection of g on x and is obtained by drawing a perpendicular from the tip of x on x. So this perpendicular represents the shortest or the smallest value of the length between the tip and the vector x. So now the issue is that g can be, so first of all, using head to tail rule, g can be represented as cx plus e. So let's look at, this is the cx and this is e. So g can be represented by their sum. But the issue is that there is no unique way of describing this g, because some of the other representations of g in terms of the x and e are shown here in figure A and B. So you can see by changing the length of e, we can have other representations of g in terms of e and x, right? So the question is, which is the best decomposition? So the approximation in the first figure is unique because its error vector is the shortest. So this e stands for the error vector, and this is the shortest for only this particular case. When this vector e is perpendicular to x, we get one unique representation of g in terms of x and e. Okay, what is c? C is the it's the weight of x. If we multiply it with x, it gives us the value of this length. So as we said, the unique way of representing is when the error vector is the shortest. So we can now define mathematically the component or projection of a vector g along x to be cx, where c is chosen to minimize the magnitude of the error vector. So the c, this one, should be chosen such that the length of this error vector is minimum. So you can see, for example, in this case c1 is smaller, so in this case the length of the vector is different. It's not the smallest length. In this case c2 is larger than c, so the length of this vector, again, it's not the smallest length. So the idea is to make c as such that it gives us the minimum value of the error vector. What is error vector? According to head to tail rule, it's g minus cx. Geometrically, the magnitude of the component of g along x is g cos x. So we know from the vector calculus that the the component of g along x is g magnitude cos of theta. Theta is the angle between the g and x, so which is equal to cx from our plot. So this is the component g. This is what we know from the vector properties, and this is cx. It's specific to the head to tail rule or the problem that we have shown here. So now, based on the definition of inner product between two vectors multiplying both sides by x, so we multiply both sides, these two sides with x, so we get cx square g x cos of theta, and we know that this is equal to the dot product of g and x. So from this expression we can write down c as the dot product of g and x and divided by x square. So this x square goes on this side, so we have this as dot product of x with itself, and so this is equal to x square, x magnitude square, as we know, and g dot x remains as it is. So it's apparent that when g and x are perpendicular or orthogonal, then g has zero component along x. Consequently, c would also be zero. So that means if this g becomes perpendicular, so you can see that there won't be any component of g along this x, and that is also proved from this formula, because the theta becomes 90 here, and cos of 90 becomes 0, and c is 0. So we therefore define g and x to be orthogonal if the inner or scalar or dot product of the two vectors is 0. So that means, as we know already, that if g and x they are perpendicular, the cos of 90 will give us a value of 0 for their dot product. So now this was an introduction or a review of the behavior of vectors. Now we shift this discussion towards the continuous time signals, which we have proved already that they are almost the same as vectors depending upon the samples that we have, the number of samples, time samples we have for the signal. So from this we'll discuss the orthogonality of continuous time signals. So we will show that it's similar to the orthogonality of vectors. So the concept of vector component and orthogonality can be directly extended to continuous time signals as well. So let's consider the problem of approximating a real signal gt, it's a continuous time signal, in terms of another real signal xt over an interval t1 to t2. So we want to represent gt in terms of xt within this interval. So there would be some multiplying factor c. So this gt is almost equal to cxt. Now this is almost equal to cxt, so we subtract this. There would be some error between these two, the terms on the left and right side. So that error term is called et, and it's equal to their difference, right? Within this interval. Otherwise, outside this interval, et, the error term is 0. For best approximation, we need to minimize this error signal, right? So if this is approximating gt, so this error must be minimum, right? If it is minimum, that means its magnitude or norm should also be minimum. So let's find out what is the minimum of this signal. So minimum signal norm corresponds to minimum energy. So if the magnitude is minimum, that means the energy of this signal et would also be minimum. So you see gt and xt are time dependent, so similarly et would also be time dependent. If the energy in et is minimum, so that means these two signals are very close to each other, right? So how do we find the energy? If we have the expression for energy between this time interval as t1 to t2. It's the integral of the square of the signal. So in this case the signal is et, so we have the square of that. We substitute the value of et, which is gt minus cx t. So this bracket squared and integral will give us the will give us the energy of the signal et. So how do we know what is the value of c, this c, which will give us the minimum value of this e? For that we use the known technique of taking the derivative of this term with respect to c and make it equal to 0, and then the value of c for which, and from this we will get the value of c for which this e is minimum. So this is what we do next. We take the derivative of e with respect to c and make it equal to 0. So this is e from this expression. Let's see what result do we get. So inside the, after, if you open the derivative, we have these terms. You can see we have a square here. So when we open the square, there is a product term, there is a square of this, a square of this term. So there are three terms, and we have the derivative of those terms with respect to c. For the first term, this is not dependent on c, so this derivative would be 0. This is dependent on c, so we'll take the derivative which will remove this c only. And again we have a term here which is dependent upon c, so this 2 will come to the front and we'll have 2c, and the rest is as it is. So and we make it equal to 0. So from this expression we need to find the value of c. Now if we rearrange it, the value of c that we get is equal to this, right? So if a signal gt is approximated by another signal xt as cxt, then the optimum value of c that minimizes the energy of the error signal in this approximation is given by this expression. In this expression, if you look at the denominator, this is the equation for energy of x. So we replace it with ex, and the rest remains as it is. So as you can see here, this is the discussion about signals, and we get a similar expression for vectors as well over here, right? So this means that signals and vectors can be very closely treated. They are very closely related. So for complex signals that are a function of t, the optimum coefficients become, so we have discussed in another video, to get a maximum value of this term, and in case of complex signals, so we should replace one of them with its conjugate because the magnitude remains same. So this product will give us the maximum value of the this product, right? Choosing one of them as the conjugate gives us the maximum value. This has been discussed in another video about complex conjugates. So complex functions, signals x1t and x2t are orthogonal over an interval t1 to t2 as long as we get this result. So if this results, this one gives us a value of 0, then we should know that x1 and x2 are orthogonal, right? Because the integral of these terms will give us a value of 0. So now we, after this discussion about the relation between signals and vectors, we now move towards the correlation between them. We now discuss the idea of correlation of signals, and this idea will be using all the previous discussion that we did. So by defining the inner product and norm of signals, we paved the foundation for signal comparison. We could consider C to be a quantitative measure of similarity between G and X, right? So remember, our original issue was how to relate two signals with each other. So this relation is determined by the similarity of the two. Such a measure, however, would be defective because it varies with the norms or lengths of G and X. If we simply use C, then we will see that let's look at this expression. The value of C is strongly dependent upon the energies of these signals. So they may not be very closely related to each other, but if their energies are very high, so then the value of C would be high, and so this is not a good representation of the similarity between the two signals. So how can we tackle this issue? We can tackle it by considering by similarity is indicated by the theta between the two vectors. So the angle between the two vectors, if we consider that, then there is no contribution from the energies of the or the magnitudes of the vectors, and so the similarity would only be dependent upon how closely similar these two vectors are. So amount of similarity can therefore be conveniently measured by cos of theta. So instead of using theta, we use cos theta. The larger the cos theta, the larger the similarity between the two vectors. So let's look at this situation. Larger cos theta means that this g and x, they have a very small angle between them, and we can imagine if this g comes down, the similarity between g and x will increase. So in other words, the cos of theta will decrease and the cos of theta will be large. So a suitable measure for, let's say, similarity is rho is equal to cos theta. This is called the correlation coefficient, and for the case of vectors, this is equal to the dot product of g and x and divided by the product of their magnitudes. Where does this come from? This is seen for the vectors from here, right? So we can see in fact this is the cos of theta, and if this product goes on the other side, it appears in the denominator just like we have it here, and we know that this rho cannot be larger than -1 and 1. So mathematically, if we substitute values, this is the range of rho. It cannot move out of this range. So two vectors aligned in opposite directions has maximum dissimilarity. So when the rho is -1, that means the similarity is minimum or the dissimilarity is maximum. So we use the same argument in defining a similarity index, which we call the correlation coefficient for signals as well. So to establish a similarity index independent of energies, sizes of the signals xt and gt, we must normalize C by normalizing the two signals to have unit energies. So we do the same thing because we have proved that vectors and signals behave similarly. So to apply this for the case of signals, what we do is we normalize this formula, so by the energies of the two signals between which we want to find out the similarity. So this is mathematically we can prove that this rho again will never exceed the limits of -1 and 1, but this can be in another discussion. So let us revisit the application of correlation to signal detection in a radar unit that we initially discussed on the first slide. So where a signal pulse is transmitted to detect a suspected target. So by detecting the presence or absence of the reflected pulse, we confirm that the presence or absence of the target. By measuring the time delay between the transmitted and received pulse, we can determine the distance of the target. So let the transmitted and reflected pulses be denoted by GT. GT is the transmitted and ZT is the reflected. So in that case, the similarity between these two is represented by this expression. It is called the correlation coefficient. You can see in order to increase the product, the value of this product, we have taken the conjugate of GT. So in this case, the correlation is 0 because the issue is that for the particular problem that we are considering, GT and XT exists at different times. So there is no overlap in time. So that's why we will get a 0 value. So we have to shift one of them by an amount of tau, by a time of tau. If there will be some value of tau for which the correlation will be strong. We not only detect the presence of the pulse, but we will also detect the relative time shift between ZT and GT. So if we kind of sweep this value of time, we will see that for certain value of time, the correlation coefficient will be high. Right, so the correct formula for this scenario is the modified integral, which is represented by this psi. It's called the cross correlation function. So this was called the correlation function rho. This one is called the cross correlation function, where you can see one of the um, signals is delayed or advanced, by time tau, and so we will get some non-zero result from this. This has been demonstrated here. So this is the time period for gt, and this is the pulse duration for zt. So we have to introduce a shift between these, any of these two, to align them in time and get a non-zero value for this cross correlation function that we have. Right, so correlation of a signal with itself. In this case, interestingly, this signal, the zt or gt, they are both the copies of the same signal, but one of them is reflected. So that is why this is also called autocorrelation. Right, so in summary, we have discussed signals and vectors, the relation between them. So we have discussed component of a vector along another vector. This has enabled us to obtain the orthogonality and cross correlation functions for signals as well, and then we saw the autocorrelation function as well.